All right, example 4 is just a little bit more complicated example than number 3, because in number 3 we solved a problem where we neglected to count the container that holds the water, right? We maybe assumed it was styrofoam and there was barely any heat coming out of it. So in this question, we're now going to consider that we have a glass beaker, we have water, and we have aluminum. So we actually have now 3 heat transfers that occur, right? So let's write down our given. And when I solve the given, I like to put this in columns. So let's start off like with the water, right? We have the mass of the water, which is 0.4 kilograms. And we have the temperature of the water initially, which is 40 degrees Celsius, right? Next, we'll go to the beaker, glass beaker. And the mass of the beaker, we'll use B for beaker, I guess, 0.3 kilograms. And then we have the temperature of the beaker, which is 25 Celsius. Okay, the next piece we have of given is the aluminum. And the mass of the aluminum is 0.5 kilograms. And the temperature of the aluminum is 37. Okay, so we need to look up specific heat capacities of each of these substances. So we have water. If I recall, it's 4,186 joules per kilogram times degrees Celsius. We need to find the heat capacity of the glass beaker, so we'll call that B. And we need to find it for aluminum. So let's go back to our table earlier in our notes. Okay, so we have aluminum here at 900 joules per kilogram degrees Celsius. And then we had water, of course, which I wrote down. Remember that value. And then what was the other substance? It was copper or something? What was it? Uh-oh, I've forgotten how it is. Oh, I'm silly. Glass beaker, of course, right? Glass. It's 837. So hopefully I can remember those two numbers. 900 and 837 are the heat capacities for each of these materials, substances. Okay, so now we're going to calculate the equilibrium temperature. Just kind of like the last problem, just a tad harder because we're trying to find the final temperature. So yeah, I personally prefer to use just sum of all the Q's adds up to 0. So there's going to be some substances that gain heat, gain internal energy, let's say it that way, thermal energy, right? And then some of the substances will lose internal energy. So they'll be, depends on what direction the energy is flowing. Okay, so we have essentially Q of the water, Q of the beaker, and Q of the aluminum all add up to 0. And so we just simply put our expressions in here. M, water, C, water, delta T, water, M, beaker, C, beaker, delta T, beaker, plus M, aluminum, C, aluminum, and then delta T, aluminum. And this all adds up to 0. I bet I'm going to have a hard time trying to fit all this in. It's going to be over 2 lines. So let me just now substitute all the numbers in here. I'll save a bit of time by writing it in. Okay, I've written it all out here. Not putting units in because it's just trying to save some space. And then I'm just going to expand it all out. So all the terms with T, 0.4 times 4,186 plus 0.3 times 837 plus 0.5 times 900, this gives me 2375.5 T. And then when I multiply 0.4 times 4,186 times negative 40, and then continue with 0.3 times 837 times negative 25, and then 0.5 times 900 times negative 37, it's going to be a negative number. Then I bring it over to the right side of the equation, and I get 89903.5, right? So now I just divide, and I get 37.8 degrees Celsius. And that's the final temperature of the whole water, beaker, and aluminum all together when they come to a final thermal equilibrium. Okay, hope that all makes sense.